Hello, everyone, and welcome to the third webcast focused on the grand challenges in socio-environmental modeling. Three organizations have joined forces to bring us to you today. The National Socio-Environmental Census Center, CICINC, the Integrated Assessment Society, TS, and the Socio-Environmental Modeling Journal, SESMO. Today, we turn to the very important topic of scale in socio-environmental modeling. The event will start by a keynote presentation based on an article published in the Journal of Environmental Modeling and Software in 2021 by Iwanga et al. The article is titled Socio-Technical Scales in Socio-Environmental Modeling, Managing a System of Systems Approach. Following this presentation, we will hear from three outstanding panelists. I would like now to introduce our speakers. Our keynote presenter is Dr. Rose Wang. I am delighted to introduce Dr. Wang. She is in the Department of Ecology and Conservation Biology at Texas A&M University, US. Her research focuses on the assessment of the potential impacts of climate change and policy on resilience and sustainability of systems of interest using SES models. She serves as a co-editor-in-chief of Ecological Modeling and associate editor of two international journals, Biological Invasions and Plant Ecology. Our first panelist is Dr. Val Snow. She's an agrosystems modeler and senior scientist at AgResearch in New Zealand. Her research focuses on the use of models to support land use policies, sustainability, and resilience of agri-food systems. She co-leads the POW-POW-T, loosely translated as Visualizing Distant Horizons, which is about developing methods to support land use decision-making and to capture multiple viewpoints and multiple well-beings. She is also an editor-in-chief for the Journal of Agriculture Systems. Our second panelist is Dr. Derek Robinson. Derek is an associate professor of geography and environmental management in the University of Waterloo in Canada. Working within the context of land system science, he uses novel models to collect high-resolution spatio-temporal data to calibrate and validate natural systems models at scale of decision-making. Using agent-based models to formalize and test our understanding of land management decisions, he always seeks ways to scale up these spatio-temporal data without retaining environmental and social heterogeneity. Our third panelist is Dr. Volker Grimm. Volker conducts research at the Helmholtz Environmental Center in Germany. He is also a professor of theoretical ecology at University of Potsdam. A world-renowned expert in ecology and agent-based modeling, he has pioneered their application, including the development of standard protocols for model description known as ODD and model development known as TRACE. Volker contributed to a strategy to make models more structurally realistic, known as pattern-oriented modeling. He has also contributed to many ecological advances, especially those concerning the concepts of stability and resilience.
Welcome to this tutorial on confronting issues of scale in socio-environmental systems modeling. I'm Xiaoxuan Rose Wang, a senior research scientist in the Ecological Systems Laboratory, housed in the Department of Ecology and Conservation Biology at Texas A&M University. I also serve as co-editor-in-chief for the international journal Ecological Modeling, whose scope includes papers describe the development and use of models of socio-environmental systems. The most fundamental scale issue in any systems model is to ensure that scale choices for model components are compatible with each other and are appropriate given the purpose of the model. Here, we see a multi-scale representation of a dynamic landscape. Suppose for a moment we were interested in modeling management strategy for controlling the balance of woody vegetation or brush versus grass in a prairie community. Rather than including leaf dynamics driven by photoperiod or landscape dynamics driven by climate change in our model, it likely would be more desirable to represent the ecologically driven changes in vegetation from prairie grass to woody brush in terms of monthly change in gram per square meter. We might summarize those changes at the community level in terms of annual changes in the relative amount of brush present, perhaps in terms of the percent of the area under the crown of brushy vegetation or brush canopy cover. That is, we will convert gram per square meter into percent canopy cover. This coarse scale representation likely would be more useful than finer scale representations, given the overall focus on modeling management strategies. Finally, we might prescribe rules by which different types of land managers will monitor and react to changes in brush canopy cover. Perhaps public land managers will monitor only once every 3 or 4 years, and if canopy cover exceeded a threshold level, they will use controlled burning to remove the brush the following year. Perhaps private ranchers will monitor every month, and if canopy cover exceeded their threshold level, they will reduce the brush by burning as soon as possible. That possibility might depend on burning regulations imposed by an organization in each county that monitors daily local weather report and imposes county burn bans, or by a state legislative organization that every 2 years reconsiders the legality of burning throughout the entire state. In socio-environmental systems modeling, coupling processes operating on different scales involves both a computer programming aspect and a conceptual aspect. The programming aspect needs careful attention, but we have software available to help us accomplish this task. The components and the processes included in the conceptual model are, of course, based on the perception and the priorities of the modelers. Thus, the scale issues encountered during conceptual model development often arise from the different scale lenses through which members of an interdisciplinary team view the model. Hence, the challenge is to establish a shared language among team members, which will allow reflection on how their different scale perceptions can be integrated into a coherent, multi-level conceptualization of a system of systems. The development of guidelines to aid in this type of reflection and integration is currently an active area of investigation by socio-environmental modelers. Scale issues arising during conceptual model development also are closely associated with differences in the scales at which the available data, information, and knowledge have been collected, and all are usually discussed. Common issues include assuring the compatibility of finer-scaled quantitative data and coarse-scaled qualitative information, as well as dealing with the lack of available data at the desired scale. Thus, scale decisions must be made within the context of the scales at which information can be collected. Transparency in the collection process is necessary to ensure that information collected at one scale can be interpreted appropriately across the range of relevant scales. During quantitative model formulation, scale issues often arise when the component models lack modularity and hence both syntactical and semantical consistency. This is a fancy way of saying that the component models lack clearly defined interfaces that facilitate the transfer of information from one model to another in a manner that does not misrepresent its meaning. The development of guidelines to aid in the modular design of models is another active area of investigation by socio-environmental modelers. Elaborating a bit more about syntactical and semantic consistency, the existence of a computerized coupling between two component models does not guarantee an appropriate maintenance of the conceptual content of the information. Turning our attention to the application phase of socio-environmental systems modeling, a critical consideration is that component models may evolve independently. Development of each component model, by necessity, is led by disciplinary experts, and most likely these models will undergo separate, asynchronous development cycles. I want to mention two aspects of these separate development cycles that affect, first, appropriate implementation of the integrated model, and second, model perpetuation and communication to stakeholders. Appropriate implementation of the integrated model may be hindered if component models evolve independently, because changes being made to one model may not be well matched with changes being made in another model. For example, consider an integrated model for control of vector-borne diseases composed of an ecological model and a management model. Further, suppose the ecological model assumes there is only one host for the disease vector, and the disease control model focused exclusively on controlling the vector on that host. If discovery of a second host prompts inclusion of this new host in the ecological model, continued elaboration in the disease control model of strategies focused exclusively on the initial host would preclude appropriate implementation of the integrated model. By model perpetuation and communication to stakeholders, we mean facilitating future use of the model and ensuring that it is used appropriately, that is, as it was intended to be used. This depends, of course, on consensus among stakeholders and the modelers as to model purpose. We focus here on the scale of documentation and the process of evaluation required in socio-environmental systems modeling. When socio-environmental systems models are used by external stakeholders, some amount of technical support and adequate documentation and user-friendliness are likely expected. Without this, use of the model and thus its impact is likely to be minimal. Now that we have reviewed scale issues throughout the modeling process, I would like to provide some general suggestions for dealing with scale issues that arise during socio-environmental systems modeling. My colleagues and I have gleaned these suggestions from our own experiences and from the experiences that others have reported in the literature. Arguably, their applicability extends beyond issues of scale per se, but we think they are particularly relevant to scale issues encountered in socio-environmental systems modeling. They include 5 pieces of advice that are simple and commonsensical. Yet, it often is challenging for interdisciplinary groups of modelers to put them into practice. First, we suggest that as a team member, you foster constant collaborative learning and reflection. Discussions along the way of how the team model building process is going will help the team build trust and ensure integrative model formulation. A diversity of perspectives on the problem at hand is a strength of interdisciplinary, intersector groups, but also is a potential source of strife. Effective and reflective communication is a prerequisite for development of a cohesive model of a socio-environmental system. In our experience, the most efficient way to move an interdisciplinary conversation forward is to look backwards, in search of shared concepts. Once we have found common ground, we can move the conversation forward along diverse disciplinary paths under the guidance of our disciplinary experts, each of whom they can explain where they are leading us and why. Related to effective communication among modeling team members is effective documentation of the modeling decisions made during team discussions. Although a variety of documentation guidelines applicable to socio-environmental systems modeling, including description of spatial and temporal and less commonly organizational scales. Most focus on detailing final scale choices. No mention is made of potential alternative scales and whether they were discarded as inappropriate or remain potentially viable alternatives. However, there has been increasing recognition of the importance of documenting the discussions at each important decision point during model development. When properly documented, the content of these discussions can provide both guidance and justification for the pathway of model development. In particular, detailed explanations supporting scale decisions can reveal the richness of thought embodied in these decisions, which otherwise likely will be forgotten. Thus, when asked by end users to explain how specific scale choices were made, modeling team members will be able to recapture the richness of their decision-making rationale. This ability to communicate scale decisions clearly increases model credibility and usefulness, and also facilitates reflection on scale decisions in response to questions about alternative scale choices. Debates related to scale decision in socio-environmental system modeling often are related to a mismatch in our perception of causality. Thus, explicit acknowledgement of the subjective nature of causality is a requisite for constructive discussion of scale issues. This new insight might suggest relative minor rescaling involving particular variables or functions, or major rescaling involving linkages among the social and environmental model component, or even modification of project objectives and the rescaling of system boundaries. By nature, our willingness to make changes tends to be inversely related to the size of the required one step back, and likely also is diminished by our uneasiness about publicly admitting we made a mistake. A cultural shift in thinking that embraces and rewards adaptive adjustment throughout the modeling process, which could be facilitated via documentation of the rationale for those adjustments, would be of great benefit in dealing with issues of scale. Embracing change in socio-environmental systems modeling entails the testing of model integration, especially the regular testing of linkages among physical, biological, and social model components. Such testing should include conceptual as well as technical aspects. The ability to write code that links model component in a computer is a necessary but insufficient prerequisite for appropriate model integration. Technical challenges to integration arise when component models have been developed using different spatial, temporal, and/or organizational scales. Often component models have been calibrated independently of one another, which, in addition to requiring the rescaling of information passed among models, may also require recalibration of the newly linked models. The new linkage also may give rise to rescaling issues within the newly linked models. Conceptual challenges to model integration are ever present, but are easily overlooked, and the conceptual aspect of scale issues can be tricky to identify precisely. In socio-environmental systems modeling, most frequent component models have been developed originally to address questions that differ from the questions being addressed by the integrated model. That is, component models were conceptualized, developed, and validated for use within different domains. Thus, their reuse within the new domain of the integrated model requires revalidation, which includes evaluation of their conceptual validity or credibility within the new domain. Regular shared language discussion focus explicitly on scaling differences among physical, biological, and social model components facilitate early identification and the resolution of both technical and conceptual mismatches, and is time well spent.
There's someone who remains anonymous who asks if you could elaborate on the idea that causation is subjectively defined. Is this always the case?
I feel this is really hard to say, but based on our experience with a few model experiences, for example, with eradication of tick-borne diseases or control or manage sandfly related disease or the sugar and aphid issue. I believe so, especially when modeler work with stakeholders or work with field biologists. We do view the questions differently. And when we decide to have everybody's knowledge all together to develop a model, I could see people emphasize different perspectives. So for example, we do ecological model. So sometimes the data is a limitation. We don't have enough data. But then if you consult with field ecologists, they feel, no, we have a bunch of data. However, when you develop a model, you try to abstract the system. You cannot really include all the detailed information in your model. So I think a good communication is good discussion is a good beginning to kind of make sure everybody know our domain knowledge, so we can integrate and choose what is the best for model objective. So I believe there is a subject causality there, but how to define this is very hard to answer.
There's one more question, then we could perhaps move on. So Takuya asks Rose, do you think it is possible for a universal language for all fields of study to be made? Or alternatively, is it only possible, or perhaps more appropriate, for a context-specific language to be developed for each model purpose?
So Takuya, I think you know me, I'm very optimistic. So I believe it will happen. But when, I don't know, I think it depends on the progress of this kind of like this webcast, right? This kind of opportunity for every discipline, the experts to get together to talk. And then right now, like CSynC promote a lot of activities trying to gather different disciplines of scientists together to discuss. And when I check the CSynC website, I noticed they have done a lot of exercise. So for example, they could have a big poster and have everybody put stickers to demonstrate the conceptual ideas. And I feel through this kind of exercise, we can achieve the goal. And another thing is, I know CSynC recently are trying to propose one kind of idea is how to translate your research idea into one page and demonstrate to the public. And I thought that that's extremely helpful. So if we could try to have all the scientists can try to develop this kind of skills, and when we have a meeting all together for one specific project, we could share this kind of concept together. And I think eventually we can have we can build a common ground. But the specific language, I'm not quite sure like how easy it will be. But I think a common idea, common concept, or using some symbols to present ideas, I think we will get there.
Okay, this is from Helene Hordeg. It takes time for a multidisciplinary group to grow in understanding colleagues from other disciplines. What is your experience, Rose?
Yes, I think this is a hard, and it depends also on the problem. Is a really urgent issue, or is more like not so urgent issue. So recently, because I work with some scientists in different areas, and I noticed even different countries, when they handle one environmental issues, they have a very different approach. So I may be biased, but I think when I see this issue happen in the United States, they will have a funding set up and quickly, and they want a solution soon. So when I say soon, the time length, I just compare with my colleagues in Europe. So their project length usually is longer, so they have time. I feel like they have more time to ponder, to think. But sometimes when the issue already happened, they are still in the developing process. And in US, it's kind of like, okay, things happen, we need to resolve it soon. So we find a quick solution to fix the current issue now. But the issue is, so I'm biased because I only deal with a couple agriculture issues. I feel like we lack of a long-term perspective in the sense, okay, we solve the issue. Can we give more funding or more time for this particular project to extend it and what they learn so we can prevent the issue later? But then like my colleagues in Europe, when they try to study the ocean water pollution, they have a relatively longer period of time. So even though they couldn't correct the current issue very soon, but they try to have the project for the long run for probably the next generation. So I think it depends on time, it depends on budget, but then sometimes also depends on how open you are. So we are very lucky. We work on the sugarcane aphid and our colleagues are extremely open. So we have a lot of discussion and we try to accommodate each other's opinion. So I think it's project specific.
Thanks, Rose. So we need to move to the second part of our event today, which is our panelists and the panel discussion. So I would like to invite to the floor Dr. Val Snow. So over to you, Val, to reflect on your experience and thoughts on how to deal with scale in SES modeling.
Thank you, Sondos, for the introduction, and Rose for the scene setting. In this presentation, I'll give an overview of the issues of scale that we're facing in New Zealand related to land use and water quality. As a forewarning, this is all about problems and very little about solutions, I'm afraid. New Zealand is unusual for a developed nation in that agriculture is still an important part of our economy. Around about 11% of our workforce is employed across the agricultural industries, and around about 90% of the production is exported, generating 2/3 of our export earnings. We produce enough to feed around about 8 times our population, which we feel is quite significant. And it is having some consequences on the environment. By many standards, our water quality is very good, but it is declining, and it's a major issue between the urban and rural populations. And in the rural waterways, farming activities are the major cause of the problems. So to control the water quality issues, land use is regulated because the water quality is a diffuse pollution problem. The primary regulation mechanism that we have in New Zealand is not prescriptive or input-based, but it's instead based on the effects that a farm is or might have on the environment. This creates some challenges and also some opportunities for modelling, because it's not practical or even theoretically feasible to measure emissions from a farm or its effects on water quality. There are no measurement technologies that are useful that are available at the useful time and space scales. Research grade technologies are either too small or too large and would be infeasibly expensive and too temperamental. We're thinking about 15 million hectares here when it comes to farming. And even if measurement was feasible, it could not account for future or planned activities. And you need this for effects-based implementation. Given this, the models that regulate nutrient losses and losses from land use activities are the only mechanism that we have to implement our overarching land use regulation. Our farming is primarily pastoral livestock farming. We use very little animal housing, and so we do not have the same sort of problems with effluent and manure that are seen in some countries. So by most standards, our land use is extensive. However, at some times of the year and in some locations in the landscape, the grazing intensity gets quite high. This particularly happens in winter when the natural feed supply from pasture is low, and farmers use a variety of mechanisms to stockpile feed for these months. Feeding the stockpile to the animals results in high animal densities, and these high densities are environmentally problematic. The crux of our problem with nitrogen movement to water is that sheep and cattle consume far more nitrogen than they need. They excrete the excess nitrogen into small, concentrated urine patches, and there's far too much nitrogen in those patches for the growing pasture to take all of that nitrogen up. So these areas become large sources of nitrogen losses to the environment. So taking that urine patch as the primary spatial scale of interest, we know that there are many biological and physical processes that are altered by the high nitrogen in the patch. Together, these operate to affect how much of that nitrogen ends up leaching. Fortunately, we've got devices that can measure leaching from the urine patches, and the combination of the measurement and the knowledge means that we've got quite good models of leaching at the space and time scale of a single urine patch. Unfortunately, a paddock on a farm is not simply a collection of independent urine patches. That would be far too easy. There is more pasture growth above urine patches, and that affects the amount of feed available for grazing. And more grazing means more urine patches. As the number of urine patches increase, the area of patches deposited on existing patches increases, and the amount of leaching of nitrogen has a non-linear relationship with the amount of N deposited to the urine patch. So all of these combine together to give a much more complicated system that becomes more complex with scale and stretches the models that we have that are quite good at the urine patch scale. We have got some new techniques that are getting better at this, so there's some hope there, but what about at even larger scales? At regional scales, here I'm looking at a catchment in the south of our country, we're seeing some major shifts from extensive grazing, which here is being shown in the light grey, to intensive grazing, such as dairy production, in the dark grey. How can we use models to anticipate likely shifts in landscapes and land uses rather? Models for this need to be based on more than assumptions of economic rationalism. Should we abandon attempting to predict shifts in land use and instead concentrate on generating a range of plausible scenarios and investigating their likely effects? Modelling at larger scales is considerably more difficult than modelling a single farm. The first problem is that the scales are not independent of each other. We are perhaps used to thinking about space and time scales and increasing in concert. At any given point, water quality is influenced by the activities at the location in the landscape near in space and close in time. But it's also influenced by more distant locations further back in the past because of time lags. So as the space scale increases, so does the time scale. But social and organisational scales also come into play as space and time scales expand. As we consider space scales larger than a farm, the relationships between farming sectors become important. As the area, as the area of dairy farming increases, so does the demand for winter grazing on extensive farms. Dairy farming also generates a large number of male calves, and they can be sources of beef animals for the extensive farms. More extensive land uses usually demand more labour. Dairy farming requires more labour per unit of land or of stock than extensive farms, and horticulture has very high labour demands at particular times of year. These labour patterns affect the local towns, adding to the population, either permanently or seasonally, demanding housing, medical and community services. Changes in land use can markedly affect these and bring additional services into local towns, so benefiting the local population. However, the reverse is also true, with de-intensification sometimes bringing devastating effects to rural communities. One current topic topic example of this is the conversion of extensive grazing farmland to forestry for carbon credits. That results in a massive decrease in the population of the local towns because of the change in labour demand. If we're going to model land use effect to support policy development, then we need to be able to capture these interrelationships. In my final slide, I'd like to draw from the two challenges outlined in the SESMO paper that I think are relevant here. The first is the need to trace phenomena across scales. For some of the examples I gave earlier, this might be simple accounting. The cows wintered off from a dairy farm need to arrive at another suitable farm type, not a ridiculous distance away. And at some point they need to move back. Conceptually, this is simple, but there is a large leap from the simple concept to automatically generating tractable rules for likely stock movements between individual farms. It gets even more difficult when the time and space scales are such that social and organisational shifts are important. Too many models are based on the assumption that economic rationality drives farmer land use decisions. Conceptually, we know that there are many other drivers and also constraints, but these are easier to describe conceptually than to include as features in a model. And if we do, then how do we link from those changes in land use to impacts on the local communities? There are some approaches for calculating economic benefits, but we know that the important parts of the story are more difficult than just economics. The second point I'd like to make is it picks up on the challenge of methodological choices and formal testing when modelling across scales. While we know how to do most of this for the time and space scales, I think most of us know, even in those models, that it's not terribly well done. But then consider the social and organisational scales. Here, the methodologies available for testing the mechanisms are much more in their infancy. As we rise to the SES challenge of better accounting for the social dimension, we will need to pay attention to the rigour of model development and application. And I, for one, really look forward to seeing advances in this space. There's a list of publications I've cited in this presentation, and I think the text is being made available, so I won't leave it up for long. In summary, I think the Grand Challenges paper has nailed it with respect to the problems and issues that I see facing New Zealand farming. At the beginning of this talk, I warned you that it's all about problems and little about solutions, and I think I might have lived up to that. I look forward to initiatives such as this seminar series sparking new approaches in this very difficult yet important area. Thank you.
Thanks, Val. Now I would like to invite Derek to take the floor. Over to you, Derek.
That's a great talk, Val, and thank you, Sandos and Sussink, for bringing me on board. It's a pleasure to be here today. And when you guys asked me about confronting issues of scale and socio-ecological models, the first thing that came to my mind is that it seems like there's a huge amount of effort at the moment, and perhaps the desire to go big. How do we scale our socio-ecological system models that represent both natural and human systems to large spatial extents? And while this remains a challenge for both natural and human systems modeling, there are ample examples of natural processes represented at large spatial and global extents. And so, for example, we can find erosion being modeled and estimated globally. And similarly, we can find examples of terrestrial biomass and carbon being modeled and estimated globally, as well as other natural processes. If we look at the ecosystem process models that are behind some of the data, like I'm showing you here with carbon estimates, and we look at those models that incorporate carbon dynamics from journals like Ecological Modeling and Global Climate Biology between the years 2006 and 2011. You can give me a hard time for not updating this figure to more current dates. Then we see that there's a variety of different scales that are represented here. On the x-axis, we have temporal scale, in the orders of days to hundreds of years. And on the y-axis, we have spatial scale in the order of plot levels, 1 hectare and up to tens of thousands of hectares. And when we look at a number of models from these two journals, we see that the vegetation dynamic models represent daily to decadal processes across spaces ranging from 1 to tens of thousands of hectares. And of course, there's other examples within this figure and beyond the literature that I looked at. But what's interesting to me is that the majority of human interactions with their environment occur at a spatial temporal dimension that's poorly represented here, which is subannual and typically localized to the spatial scale of individual property parcels or fields and areas within a property parcel in rural landscapes. It's equally surprising to me if we take a similar figure representing models of land use and land use change, that they rarely operate at the subannual level. They do typically represent activities within property parcel boundaries, but again, they don't have this subannual piece, and we've all had experiences both in our own lives and with farmers and with businesses, firms, other sorts of actors that are making decisions much more regularly than annually. So these points are relevant, I think, if we want to model socio-ecological systems, because we have to be able to represent the interactions and feedbacks between the natural and human systems at the scale at which humans interface with their environment. And I think we have a long way to go. In the past, I've interrogated ecosystem process models that fail to account for the effects of size, shape, and the amount of edge for habitat patches, the patterns of which are driven by humans. And we know that these patterns in our ecosystems affect the processes within them, and subsequently the habitat conditions that are appealing for different types of species. More recently, I've been interested in agricultural systems and linking models of human behaviors to natural system models to represent the effects of land management choice on surface runoff, erosion, and nutrient loss, and the effect of those processes on subsequent management behaviors. Now, as I started coupling these simple models of erosion to an agent-based model of agricultural land management, it quickly became apparent that there was a pretty big lack, a very big gap in the validation of erosion models at the field scale, which is the scale that humans are making decisions about how to manage their land. Instead, erosion models are typically run at river basin and watershed scales. They're calibrated to pour point or stream flow gauges that poorly relate to the individual farming units that comprise these watersheds. And I use this image here just to emphasize my point about the watersheds and the focus on hydrometric stations and pour points. But this paper is actually focused on winter stream flow, but the flow is a function of what's happening on the farm fields. Furthermore, the majority of empirical erosion work is represented at the plot scale. So it's a very, very small scale relative to 40-acre fields. Or they're based on crude relationships with satellite-based data. And I couldn't in good conscience continue trying to model my socio-ecological system without finding a way to make sure that my natural system models of erosion were validated at the field scale. Now, I'm a big proponent of toy-based models and models that offer proof of existence, but the lack of data and research in this area was really surprising to me. So I set out with my students, and we repeatedly collected terrestrial laser scanning data, remotely piloted aircraft data, and a wealth of ground control points to make sure we had the highest level of accuracy. And we started quantifying surface changes and surface change detection over a year and a half of erosion and land management on a farm field in Southern Ontario. These data enabled us not only to calibrate and validate erosion models at that field scale in a semi-distributed manner, which I'd argue hasn't really been done before, but it's also highlighted through discussions with farmers across a multitude of sites that the coarse resolution data and the outcomes of models that use those data don't coincide with what farmers are observing on the land. So in this series of panels on this figure, Panel B is showing a 2-meter regional digital elevation model with flow accumulation pathway collected on there. Most of the time, those data are represented by 10-meter, 20-meter digital elevation models. Here, we have a really fine resolution 2-meter DEM. And the farmer would argue with me if I showed him this particular outcome. It seemed like it's breaking through the berm at the top of the figure. It's also much more intense along the dominant flow pathways, and it's failing to pick up what they see when they're out in the field in the rain, which is the flow along the interrill passageways from the tillage. So if we look on the right-hand side at panel D, now we're picking up the flow accumulation along these tillage pathways with a fine 5-centimeter resolution set of digital elevation model from our unmanned aerial vehicle or remotely piloted aircraft. So I think as we're confronting these issues of scale in our socio-ecological systems models, I'm going to argue that we need to do more to calibrate and validate natural system models at the scale of the human decision makers. And I'd say if we can't calibrate and validate our natural and human system modeling components independently, or when they're coupled together at the scale of the human decision maker, then I think the relevance of our models and our science to society and our contribution to society is diminished. I say this because I think we have to be able to demonstrate the impacts of human activities at the decision-making scale in order to encourage behavioral change. So with the limited time I have left, I'll acknowledge the known challenge on the human side, which is where I started out, in that these efforts to go big, these efforts that are associated with scaling up behavioral models to large spatial extents. There's no doubt that this is a huge challenge, and one that a number of people and groups of researchers are trying to tackle and taking on. And the fundamental issue that's confronting them is that while there's a rich body of conceptual studies, as well as local case studies in different environments, they're documenting how local contexts and land use decisions are made. There's no global overview of how these characteristics and attitudes influence land use decisions around the globe. And this is work that Malik and Verberg, among many others, are trying to change and are doing and trying to change the situation for us all. So I could get into why we want to do this sort of thing, scale up to large spatial extents, our socio-ecological models, or provide reasons why generalizing human behavior is challenging. But I think we're going to find that many of the answers lie in the literature of our next panelist, Volker Grimm, in the use of pattern-oriented modeling. So what I try to do is I try to look at some of the large-scale modeling work of Robert Axtell and think that our coarse resolution census, remote sensing, and other data are providing patterns for which we could and should be able to get our models of human behaviors to reproduce. In a recent webinar with Robert Axtell, remembering this correctly, but he noted that you only need a small amount of variation in human behaviors to generate observed patterns. Of course, there's different degrees of error associated with those outcomes. And the idea and point that he made was really impactful to me because it thought of some prior work I had done with Dan Brown, where we observed that only a small amount of variation in human behavior was required to generate substantial differences in spatial patterns of urban development and agent performances, as well as the socio-ecological pathways that the land use change underwent. And this too is what we observe in our erosion-based modeling. When we look at standard approaches as shown on the left with some coarse digital elevation model data that fail to capture field boundaries, ditches, and other human features, and they yield substantially different results than when we focus at the scale of the decision maker at the property level. On the right-hand side, we've digitized over 60,000 farm fields. And we've included all the connectivity features between those farm fields in order to see how much of a difference does it make when we actually focus on the human system and then implement that natural system within the human constraints. So I think I'll leave off with my two thoughts for today's lecture, which is that we should ensure that we represent our natural processes accurately at that decision-making scale in our socio-ecological systems models. And I think we should be less reluctant to scale up to large spatial extents and be more supportive of those that are blazing the trail in this direction. Thank you.
Thanks, Derek. So now I would like to invite Volker to the floor. Over to you, Volker.
Yeah, this talk will now assume a little bit of a conceptual attitude. All this here has been said, and I can summarize this on the first slide. We have this multitude of skills, we have organizational skills. But one first remark I would like to make, that we often speak of linked systems, but since I'm involved now in a project which I mentioned before in Sweden, we very much emphasize this intertwinedness. They're not just linked, they're really, you can't separate them. And this is, so to say, at the core of the idea of John Little and others of the systems of systems approach. We're actually talking about one system with certainly subsystems, which within their subsystems have strong links. But for many questions, as also has been mentioned by my previous speakers, we can't really separate them because they're all these feedbacks. But on the positive side, when you think about it, if the social, ecological, or social environmental system is just another system, we might actually transfer some of the experiences and the insights we gained from more domain-specific modeling, transfer it to this integrated modeling and scale issue field. And this is what I'm trying to do here today. So again, this has been said by all the speakers before. The key question is, how can we make sure to capture the relevant scales and the interactions? And the key idea is that systems are characterized by patterns observed at different temporal, spatial, and organizational scales. Pattern I use in a very broad sense. You can also call it regularity or signal or anything which is beyond random variation. I like this quote very much, made by a forest scientist many years ago: change without pattern is beyond science. So this is not my invention. This is what scientists are doing, right? So for example, these are very famous examples from the physics for the natural sciences, right? So everything we know about the universe for many years was just based on the patterns which people saw on the light emitted by galaxies and stars, right? Like this redshift. Or quantum physics. Yeah, people saw patterns in the light emitted by atoms. And from these patterns, they inversely try to figure out how matter actually is organized. Or the mass extinction, there was a pattern in some sediment layer with an unusually high concentration of a certain isotope of iridium. Or if you read this book about the discovery of the structure of the DNA, it's a kind of a textbook on how people combine different patterns to find the right structure, which was then the double helix. People knew it would be a helix, but they didn't exactly know the structure. So this basic idea of using characteristics of systems and then inversely try to determine what is the underlying cause, what's the organization, that's very, very, it's the heart of science, isn't it? So pattern is beyond random variation. In population dynamics, you could think of a very striking pattern. We could say, like, see cycles, for example, in small mammals or lemmings or forest insects. But you could also say, well, I have seen abundance between 30 and 60 per hectare. This is also a pattern because it's still some information that the system is not going below 30 and not going higher than 60. So these patterns contain information about the internal organization, and we develop models to reproduce these patterns and to identify the real systems organization as good as we can. So as a scientist, we kind of need to squeeze these patterns and try to inversely decode them and see the underlying causes. So here are patterns from ecology. This panel here on the left is the movement paths of lynx released from the Harz Mountains. This is the output of a model. This is all outputs of a model. This is the growth of a microbial colony on an agar plate. This is a so-called banded vegetation patterns, which you sometimes see in semi-arid regions with certain topographic properties. This is a forest fire map. So the color indicates when was it the last time that this plot was burning. And all these patterns have been reproduced by these models, and all these patterns then have been used to inversely determine what is really what are the driving mechanisms which characterize these systems. This is more from the social science and very stylized models. It's about opinion dynamics, where opinion is scaled between +1 and -1. So these are the extreme opinions, and you have a more neutral opinion here, and then you can develop model under what conditions do we really see that the opinions are moving more to the extremes, and almost nobody anymore is in the middle. So people use this all the time. That's clear. The challenge with complex systems is that the single pattern will usually not contain enough information to inversely determine the underlying mechanisms. This is a very famous time series of almost 100 years. It's from the Hudson Bay Company. It's the abundance of lynx, and it's the abundance of its main prey, the hare, the snowshoe hare. And yeah, you see cycles, right? And there are many, many different models have been developed and proposed to explain these patterns, but they're all based on different mechanisms. Yeah, and the reason is it's just too simple to have a model which produces cycles. Yeah, you just need some time delay in the regulation and you will have cycles. So how can we find out which one of these models is more close to the real organization of the systems? And there are some on the market. I won't go into detail here, but this is one example that a single pattern might not contain enough information. So the idea of pattern-oriented modeling is a very, very simple one. Just take into account multiple patterns. So these are observed at different scales in time and space, and also at different levels of organization. It might be behavior of households, it might be behavior of an entire community. And then make your model reproduce these patterns simultaneously. Yeah, so make it harder for the model to pass your validation test. So in a way, you use each pattern as a filter to reject unacceptable submodels or unacceptable parameter values. So we have called this pattern-oriented modeling, but I can't emphasize enough that this is what experienced modelers within domains are doing anyway. But it's really important to make this an explicit and conscious strategy. The good news, I mean, Rose mentioned this at the beginning. People are talking about, well, for this social ecological system models, linking different scales, we need more data. Yeah, so and everybody's complaining about we don't have enough data. But yes, it would be good to have good data sets, but we certainly cannot wait until we have them. And the good news is that sometimes even qualitative data can be used to very, very good benefit. And I always give this example here. Imagine you have to pick me up at the airport. And a data-rich pattern, really with strong information, would be just a photo, right? Because this contains all the information, all they look like. You have the photo, you look at the people coming out of the gate. Hi, Dr. Graham, here you are. But now let's assume we don't have the strong data about land use, about runoff, about whatnot. But we have some weak patterns which might by themselves not be very informative. But if you combine them, you still very quickly come to the point that you can identify me, or in the case of your systems model, the dominant processes in your system. If somebody tells you, yeah, Dr. Grimm certainly is male, yeah, that filters out about 50% of the people coming out of the gate. He's 60-ish, well, that's another filter. He has a gray beard, that's another filter. He's tall, that's another filter. And I'm 100% sure that you would identify me easily with these 4 really, really weak and not very informative patterns. That's the basic idea of pattern-oriented modeling. Of course, if you have such strong data, you should use them. But if in some subsystems you don't have this strong data, you could think about these weak patterns. Here's an example from oceanography, marine modeling. It's from a paper from 2008. You might have data about the stomach content of some fish. You can see they have eaten sardines and anchovies and whatever. You might have a size distribution at the population level. You might have a spatial survey about something. At the community level, you might have a spectrum about the size spectrum of the entire community, not of the individuals. You might have some catch data, which provides some information. You might, in the catch data, you might have some information about species dominance, depending on the temperature. And again, each of these single patterns might be quite uncertain, might not contain enough information, might not be suitable to filter out the right model or the best model. But if you try to combine them, you are more likely to come to the good result. And in oceanography, people already for 20 years actually speak of end-to-end models. They say it doesn't make sense to only focus on the population level and leave out details here and details here, or only at the community level, or only in the individual level. They say we need end-to-end models, which is another way of saying we need to take into account patterns at all levels of organization, so at all relevant scales. This is a recent paper which summarizes how patterns have been used in ecology. And pattern-oriented modeling, I think this is the conceptual phase, which Rose mentioned. So when you conceptualize the model, if you collect a set of patterns which you want your model to reproduce, you have to provide the entities and the state variables and scales so that in principle, the same patterns can be observed on the model. So if I have some patterns in age structure, age has to be a variable. If I have a spatial pattern, the model needs to be spatial. If I have some information about the income distribution of the farmers, of course, the income has to be a state variable. Yeah, things like that. And then I won't go into detail with the two other points. You can then use these patterns to contrast alternative models of behavior, for example, plug them into your full model and see which of these behaviors leads to the best overall fitting of the patterns. And the same with parameter sets. And I will give an example of that in my last slide, which is this one here. That was a model developed a while ago by my colleague Thorsten Wiegand and colleagues. And they wanted to model the spread of the brown bear from Slovenia back into the Alps. Due to new regulations, this was possible. And there was a population model, an age-structured population model, spatially explicit, with actually the movement of the bears. And they had a quite high parameter uncertainty. You can see here the prediction of the population growth rate, which is the red bar here. And the black bar here is the coefficient of variation, so a very uncertain prediction, so actually not usable for any practical purpose. So they were asking, how can we reduce this uncertainty? So they generated from the unknown parameter random combinations, in this case only about 600. In other cases, they use 10,000 or 100,000 parameter sets. And then you run the model for all these parameter sets, and then you compare the model output to the set of patterns which you have identified before. Of course, there are some technical definitions behind what constitutes a pattern matching and what not. So the technical details I won't mention here. And they had 4 spatial patterns, which were pretty vague. And obviously, they did not contain very much information. So of these 557 initial parameter sets, almost all of them reproduce this first pattern. So this pattern was not a very good filter. And also 2, 3, and 4, well, yeah, they filtered out about 400 of these parameter sets, but still the uncertainty was still too high, which you could see here. Now this pattern number 5, which was a time series about a certain structural index of the population structure, that one was very hard to replicate with these parameter sets. So only 12 of them made it. So this pattern obviously contains very much information. Now imagine you wouldn't have had pattern number 5. Yeah? And now you can see if you combine pattern 3, 2, and 4, actually they have almost the same filtering potential as a strong pattern here. And as a result, at the end, when you look here, you have, this is the final prediction of the population growth rate, and this is the remaining uncertainty in the parameter values. So that's the basic idea of pattern-oriented modeling. So use this information, include weak patterns, combine them. And I think this is for the systems of systems approach, one way which could move us forward. So my advice be go pattern hunting, like mushroom hunting, go pattern hunting, ask yourself, with all these collaborative approaches which Rose has characterized, so which patterns characterize the social ecological systems of interest? And even if there are no hard comprehensive data, weak patterns are very likely to exist. Just be aware of them and don't throw them away from the beginning. And then, of course, when you sit together, list all the patterns that you or the team could find. And of course, you have to prioritize. You can't make a model reproduce. Yeah, you can. There are examples, but usually it's a handful, 5 or so. I have seen also models in microbial ecology where the people have 90 or 100 patterns. These patterns determine the entities and scales that need to be represented in the model, and then use this strategy, run the models for all the different parameter values and submodels, and use these patterns to inversely determine the appropriate process models and narrow down parameter and structural uncertainty. Voila. Yes, I know it's not easy, but what is? I think this is a very broad strategy that some of us intuitively are using, but if you would do this more systematically, it may help us in the systems of systems approach and to solve the issues which have been addressed here before. Thank you.
we have one from Jan Bacchus, and I think this goes, well, this goes back to Val's presentation, I believe. Jan says, fine-grained modeling may still require generalizing the results in order to produce an assessment with robust findings without questionable or distracting details. Maps are often too powerful and slightly differently framed. If models are being used in regulatory assessments, such as environmental impact assessments, how can developers prevent results of fine-grained modeling being used in an absurdly detailed fashion? Now, who would like to take that on? Should we start with Val?
Right. Yes. Not, an easy one to start with. In our setting, I'm not seeing this as being too much of a thing that really happens. There do tend to be a lot of fine-grained maps and fine-grained modelling, but once it starts passing through a policy lens, and particularly thinking about the difficulties of trying to convert that information into something that could be an implementable policy, which means being able to set the decision framework and figure out how you're going to assess whether individual farms have complied or not against the policy, then it tends to filter out some of those more detailed or fine-grained mapping type efforts. What I do, however, like, I'm not saying this has happened, but I really liked your talk, Volker, and it made me think about things in a slightly different way. And maybe the what we should be doing is interrogating some of those more fine-grained maps for patterns, and making sure that the more summary type models or coarser grain models are going to reproduce the same general patterns, and maybe that's a way to make our models more robust in this type of setting. So I'm not sure if I'm really answered the question, but something around the edges of it.
Yeah, I would have a question to Derek, if that's possible.
Sure. Do you want me to? I can chime in on the last question as well.
Please, go ahead.
First, Jan, I think in the first part with the questionable and distracting details, I agree completely that I don't think we can use a single case study to infer broad outcomes. But I think we could use a set of fine-grained studies to provide benchmarks to know the level of uncertainty or error in our modeling approaches, and the data that they're using when we are applying models across large spatial extents. And I think if we don't know that error, then we're lacking the foundation that can be used to determine our level of confidence about our modeling results, so that we can make suggestions about how behavior should change or policies we should implement and that sort of thing. On the second part of your question about how can developers prevent results of fine-grained modeling being used in absurdly detailed fashion? It's kind of a fun question, because how can we stop anybody from misusing and abusing our models? And I like it for that reason. One of the things that I would like to see more of is that we're doing a better job of making our models not only freely available, but easy to use and replicate. And again, I'm going to also say, I love your work, Volker. All your replication work, in addition to the pattern-oriented modeling work, is so important. And I think we need to do a better job of documenting and making our models runnable, so that we can make sure that our models aren't abused.
So we have Margaret Palmer from SASync, who says that she would be interested in comments from any or all panelists on some of the following. I'm interested in the relative importance of, or in what context each may be relevant, the following as the reasons we have difficulty in modeling cross-scale interactions or SES system dynamics in general. One is our lack of understanding of the dynamics of SC components, for example, agents, decision-making, and underlying drivers. And two, variations, heterogeneity in dynamics, even for example, between individual decisions within a category of agents. And 3, lack of data. How does that sound?
I mean, I think everybody knows that modeling human behavior is the real bottleneck, and people are working on it very, very intensively, and even more and more reviews on this, which indicates that it's in a very active field. There's no final answer to that. But I mean, we always have to remind decision makers that whatever decision they make is based on their conceptual model, right? And so my take is always that, I mean, pattern-oriented modeling is not the cue to everything, right? But if, for example, in ecology, we have a model of fish behavior, we don't actually know what they do, we can implement alternative representation of their decision algorithm, plug them into the full model, and can then see which one of these submodels is leading to the best results in terms of reproducible patterns. That's a very broad strategy, and this has not been used very much so far in human decision making. That could be one way to narrow down the structural uncertainties there, but I will be curious to see that.
I might jump in there. So I think one of the challenges is it's a combination of Margaret's option 1 and option 2. That we know that we don't understand the dynamics, particularly when it comes to human decision making and responses to drivers. We can get broad responses and things like that from historical data, and then we have to assume that they still apply in the current sense. But what we don't tend to get is the variation and heterogeneity between the individuals in that population, because generally that data is at some sort of aggregate level. So trying to figure out how to disaggregate that is often taken as a step too far, yet we know that the heterogeneity is one of the things that's driving the outcomes. And we can see that in our land use change models and all sorts of things like that. So I think it's a combination of 1 and 2, and perhaps more time, more pragmatism, more trying different approaches, and throwing away the ones that don't work in that circumstances is the best approach.
I was just going to say that, I mean, there's so much we could talk about those 3 points for a half a day easily. You know, I mean, there's lots of exciting work that we need to do in terms of looking at the cross-scale components and the relationship between agents' decision-making and institutions. And I know there's a lot of work at the institution level. And so I think there's some tension where researchers are trying to either represent institutions or larger spatial units as individual agents, or as the cumulative outcome of voting and the characteristics of a population or populations of agents within. And I don't think we have a number of good examples at the upper level where we've got agents representing individual states and provinces or municipalities interacting with each other. Instead, we're still focused at this conceptual level of a local area, and then all these points of Margaret's all fit together, because then there's a lack of data, and there's a lack of types of data that enable us to represent those interactions. We don't collect those types of data, and for me, showing the drone work, that was an epiphany, because the drone data enabled me to bridge the scales between these erosion pins. All of these erosion models are based off of USLE field experiments where they have an inclined plane of 122 meters, and they're measuring the movement of soil down these very rudimentary standard landscapes, slopes. And then the empirical work is go put a bunch of pins out and let's measure how much erosion builds up over time. Well, obviously we can't fill a field with pins. And then we look at the other scale, and we've got satellite data coming in some cases 1 meter or 5 meter, where we got Iconos and Spot, and we were able to bridge this and go temporal regularly with a UAV or a RPAS. So I think we need to look to identifying some new ways to collect data and new types of variables that we don't think about.
Well, unfortunately, this is all what we have time for. So thank you for all our panelists for the stimulating discussion. This was very useful. I personally learned a lot. And thanks, Rose, thanks, Volker, Derek, and Val. And thanks for our sponsors, Sync TS and SESMO.